So here's a brief explanation of my code. I am using screenshots since my computer can handle the screen recording while having Rust opened. So basically here we're gonna have our libraries, including NumPy and, well, for the quaternions and the structure from the float32 and the conversions and the autometry. So basically we're gonna start by declaring the variables. So these ones are gonna be one for each one of the differential equations. So it's gonna be the position in the x-axis, in the y-axis, and of theta, the velocity, the omega, and, well, the wheel radius and the wheelbase, which were already established values. So this is gonna be for it to start everything at 0, and then depending on the key that we're pressing, they will change. But, well, then we're gonna declare the messages that we're gonna use. So we have the post-TF transfer stamp and the autumn messages autometry, which well, basically here it is created for broadcasting the robot's transformation, and, well, in the TF3. And, well, the autometry message, it encapsulates the position and the velocity information, and, well, these messages they're going to be critical for the inter-node communication from our ROS. Then we're going to have the initialization of the post TF from the position X, the position Y, and the position of theta. And we're going to declare which one is going to be the header and which is going to be the child. So here basically the parent frame is going to be autumn and the child is going to be baselink. And these configurations will be the reference frames for all of the subsequent position updates. Then we're gonna have our callback, which we're listening to the incoming velocity commands from the topic, which is cmd_vel, which we're gonna see later on. But basically, when a new command arrives, we update the global variables from velocity and the omega, and this will represent the forward or the rotation of the speeds, and the movement of the speeds. Then we're gonna have our main loop, which basically in our main block we are initializing our Rust node, which is called b1 sim, and we're starting the position and the orientation, which is the position X, the Y, and theta, and all three of them, the initial position is going to be 0. Then we're gonna put the rate at 200 Hz so we can ensure a high frequency update, so we can see it as smooth as possible. And, well, we're gonna register our shutdown command and initialize our transform, which is from up, and our subscribers and our publishers, which are gonna be given by the publisher of the autometry, which is given by the topic autumn, from the structure autometry, and the queue size of 10, which the queue size is the amount of values that it is saving. So it is basically well, yes, it's saving the values for the use. So depending on the queue size that you put is going to be the number of values that it is going to save for further working, basically. And, well, for the left wheel and right wheel, we're going to use the structure of float32, also with the queue size of 10, so it can save some data in the transitioning from one point to another. So it has values in which it can smoothen the transition from the kinematic equation from one place to another. And, well, basically here we're gonna just declare that the transform broadcaster and the left wheel and right wheel messages, that we're gonna make them equivalent to our float32 structure, which will be published afterwards. So basically here we're just determining the structure from the float32. Then on our while loop, we're gonna have again, we're gonna determine, this is gonna be the cycle that is gonna follow. So this is the main loop. We're gonna be integrating here the Euler's equation for the smoothing from the kinematic equations, and we're gonna define them also. So basically here we're gonna put dt, which is gonna be the the time step between each one of them. So well, this is going to help us integrate the differential equations and use Euler for the smoothing. So basically, we're going to have the position in x, which is given by the linear velocity times the cosine of theta times our time step. Same for y, the linear velocity times the sine of the position in theta times the time step. And for theta, the position in theta is going to be equal to our omega times the time step. And well, here we're going to initialize our transformation messages, which basically, after we update the pose, we are going to convert the orientation of the angle into a quaternion. So this will help us make that transition from one point to another without any singularities or moving directly. And well, basically here we're just defining the translation from the position in x is going to be equal to our equation, which is given here, and our position in y, the translation in y is going to be equal to the differential equation also given. And in theta we're not going to use them, so we're going to establish them as 0, and then for the rotation we need to add the x, y, z, and w for each one of them. So as you can see here, q is given by the equation from the quaternion from Euler, which will have one for each frame, so x, y, w, and zeta. And then we're gonna transform our send our transform, which is gonna be the pose TF, and we're gonna have our autometry sent, which here basically we're gonna build the autometry message, which includes the robot's position, as I mentioned earlier, and the orientation, which again will be translated into a quaternion from Euler. And as you can see here, we have the orientation also in x, y, z, and w, and it's also going to be equal to the differential equations defined earlier, so it knows where to apply the changes and how to apply them. And well, it will represent the measurements, well, yeah, and basically here at the end we're just adding these covariances, which we're gonna put at 0, which will basically, these are for more complex navigation systems, and we're not gonna use them, so we're gonna establish them as 0. And finally, here we're gonna have the equations for our velocity commands. So here we're gonna transform the high-level velocity commands into individual wheel speeds given by the variables from the right wheel and the left wheel, and we're gonna calculate the angular velocities from each one of them. So this will ensure if the robot is gonna go straight, it's gonna turn. So if one is gonna go faster than the other. And finally, we're gonna have these the wheel speeds are translated into packages, into messages, and they are published by WR and WL. And for the float 32 to work, we're gonna have to put these published messages. So this, if you remember earlier, we have here the float 32 defined for the pop right wheel and pop left wheel. So that is the same that we're gonna use for declaring the publishing. So we're gonna publish that messages, which is given also by the package saved on the data from the equation, from the equivalency from the right wheel, which is the equation from the angular velocity. So that is going to contain the information from the packages. So here I'm going to explain my code in screenshots, since my computer can handle screen recording and ROS at the same time. But basically, firstly, we have our libraries, which include the NumPy for the calculations, the standard messages for the float32 structure, and the quaternion transform broadcasters, and our conversions. Then we have our set of variables to be used. So here we have one for each of the differential equations, which is position in x, position in y, and position in theta, and the velocity and the omega. And well, here on the for the solving of these two, the velocity and omega, we're gonna have the wheel radius and the wheelbase, which are already given from the presentation. So here basically we're gonna declare the messages that we're gonna use. So we have the transform stamped and the autometry. So these two will basically broadcast the robust transformation on the TF tree, and it will encapsulate the autometry message will encapsulate the information from the velocity and the position, and well, it's gonna be for saving those data. Then we're gonna initialize our TFs. So here basically we're gonna set up the parent and the child frame. So we're saying that autumn is gonna be the header, and the child frame is gonna be baselink, and this configuration basically establishes the reference for all the subsequent positions and updates. And well, here we have the callback, which is basically gonna be later on we're gonna see where the CMD vel topic is, but it will basically listen to the incoming velocity that that topic is given, and well, when a command arrives, it will update that global variable of velocity and omega, and well, that will represent if it's going forward, if it's rotating, and the speeds basically. And then we have the stop, which is just for stopping. And then we have our main code. So here basically we're just initializing our node, which is going to be d1 sim, and we're going to set up our initial positions. So for x, y, and theta, for the three differential equations, we're going to start at 0. So that's going to be the initial position of our robot. So then we establish the loop rate, which is going to be at 200 hertz. And well, this is only to ensure like a high frequency, I guess. It was already given by the template the professor gave us. So well, then we're gonna put our shutdown command, which is gonna just stop, and we initialize our post TF, which is gonna set up our publishers and our subscribers, which are over here. And well, here is the publisher for the autometry with a queue size of 10, and the right wheel and left wheel with the queue size also of 10. So the speeds of the queue size of each one do matter, and so the queue size will basically be the number of data that is saving. So depending on how big it is, it's going to be the data that is saving from the transition from one point to another from our kinematic equation. So then we're gonna have our broadcasters, and we're defining our float variables, which are gonna be the structures in which we're required to send the messages. And well, now on our while loop, here on our while loop, we're gonna have, so here on our while loop, we're gonna have, firstly, we're gonna determine the delta time, which will be 0.01 in my case. And well, here we're gonna apply the Euler's methodology that I explained earlier for the transition from kinematic model to a dynamic model, or for smoothing the changes. And well, here basically we're performing the tasks for each one of the differential equations. So we have the position in x, which is equal to the linear velocity times the cosine of our theta times the time. And well, basically the same for the y axis, the linear velocity times the sine of theta times the dt. And for the position in theta, we will only multiply the omega times the dt. And well, here basically we'll have the transformation messages for the position of the robot, and basically the raw speed time now, which is always needed. Then we have the quaternion from Euler, which well, it will help provide us with a representation of the rotations, and will avoid any problems or singularities we may have with the model. And well, basically this will ensure that our entire ecosystem will be in sync. And well, same for the autumn messages. So the odometry messages will include the robot's position, the orientation, and it will be converted into quaternion. And we're gonna establish the covariance values, which were recommended to put in 0, which are for more advanced applications, in which we will have to take into account some crucial data and some other functions that we're not using right now. And then we have our wheels velocity. So here we calculate the angular velocities of the right and left wheels, and well, this only will ensure that the robot goes straight forward or it rotates. Here we're going to have our wheels messages transformed into data, which we're going to be equivalent to our variable, which we're going to use to publish our float32 variables. And that's basically a general explanation of the code. So here is the code working. So the libraries and everything that I explained earlier. And well, we're gonna run it using the launch file. So here it is. Here we put the launch file. And we're gonna have our robot. So basically, to see the float32 messages from the speeds from the left wheel and the right wheel, we're gonna use this raw topic echo, which are gonna show the position, the velocity of each one. So same for the left wheel. And basically here, when we give him some, for example, here it's gonna have one wheel spinning faster than the other one. So as we can see, the right wheel should be faster than the left wheel. And as we can see, it is working. Then if we give it a straightforward direction, it should be the same number. So 8 for the right wheel and 8 for the left wheel. And well, here is gonna, there's our robot. And well, we can control it with the keyboard. And the data of the float32 messages.